Hi, everyone. Welcome back. Really nice to see everyone again after a year. So this is, this is both a reunion workshop and a kickoff for the summer cluster. So it's, for that reason, it's going to run slightly differently than a reunion. So the talks are going to be recorded, not streamed. So and then the other thing is there's a really great lineup. I think Nico and Anurag worked really hard on making it so, but it's a particularly exciting time in the field, both because of the experimental work, but also because of there are lots of great theoretical breakthroughs and everything in the middle. So this week focuses on many aspects of it: fault tolerance, crypto, algorithms, and complexity. I should say one last thing. Last year's semester, as well as this summer cluster, they're part of this quantum pod here at the Simons Institute, and it's all supported by NSF and DOE. And I think, as always, but also especially these days, they like to hear what actually comes off all the funding. So, do acknowledge this in your papers, and do let us know. So there'll be some email. I don't think you'll be bombarded with it. Maybe there'll be 1 or 2 emails, but do respond to them. Okay, thanks a lot. And so let me turn you over to Nico, who's leading the charge.
Sure. Yeah, thanks, Umesh. Welcome back, everyone, also from me. As Umesh already said, this is the reunion of last year's program on quantum fault tolerance, quantum algorithms, and complexity. But it's also the start of the quantum program, so also welcome to everybody who is joining that. We have a nice schedule, I think, for this week, and we are starting off strong with Thiago, who will tell us about rapid mixing for Gibbs states within the logical sector. Take it away.
Cool. Thank you very much, and thank you all for having me, and for coming for the first session on Tuesday. So great. So I'll be talking about some upcoming work on rapid mixing for Gibbs states within a logical sector, and this is based on joint work with Reza and Yunchao. Broadly speaking, our work is on the dynamics of self-correcting quantum memories. And so just to make sure everyone's on the same page, I wanted to start with some basic background in quantum error correction. As I'm sure pretty much all of you are aware, in the standard setup in quantum error correction, the goal is to encode some quantum state psi. And to do so, I'm just going to append a bunch of ancillas, initialized to all zeros, which in some sense are storing the syndrome of the code. And in a very precise sense, our logical information is being stored into the degenerate ground space of some code Hamiltonian. Now, if this Hamiltonian isn't too explicit to you soon, don't worry, I'll present some very concrete examples in a bit. With that in mind, what is a self-correcting quantum memory? Well, in some sense, self-correcting quantum memory departs from the standard setup in quantum error correction in that we're encoding a state psi into a mixed state. Now, precisely what I mean by that is that I'm going to have my logical state psi, but I'm going to append a specific distribution over syndromes. And I'll denote that distribution over pi beta, as pi beta. Now, just to be slightly just to give a slight more explanation, you can interpret the Gibbs state of the code Hamiltonian that I mentioned earlier, in some sense as thermal noise applied to a random ground state. And in that picture, this Gibbs state, or with a specific state inside, is applying that same thermal noise, but to a specific ground state. In some sense, confining your Gibbs state to a logical sector of the Hilbert space. And I'll refer to these states as Gibbs states within logical sectors. Now, what makes this self-correcting? In a very precise sense, a self-correcting quantum memory is nothing more than a Markov chain which doesn't mix quickly. Now, what I mean by that is we're going to model noise or thermal noise on our error correcting code using some Lindbladian L, which you can just, for all intents and purposes, interpret as a quantum version of a Markov chain, or just some quantum Glauber dynamics. Now, if you were to apply this noise process to your memory state for a very long time, in particular infinite time, you would eventually get to the Gibbs state, like in some sense decohering your quantum information. However, what makes it self-correcting is that if you apply it for any sub-exponential timescale, like e to the n to the c, where n is the number of qubits, then your state is approximately stationary. It just doesn't degrade the quantum information for a very long time. In some sense, like a passive form of quantum error correction. Now, this might seem a little abstract, and I'll come up with some examples in the next slide, but is at least the qualitative definition clear? And I should have said in the beginning, this is meant to be interactive. Feel free to chime in with any questions.
What are the assumptions you're making about the Lindbladian?
It's local and detailed balanced. You should think of like a Davies generator with single site updates.
Why do you call it self-correcting rather than just stable or something?
Historical reasons. But yeah, it is essentially like passively stable. Like it's almost as if your code had a local decoder. Great. So let me be a lot more concrete. The canonical example of a self-correcting classical memory is the ferromagnetic two-dimensional Ising model. Now, for the uninitiated, this is just a lattice of spins in 2D where I'm going to place bits on each lattice site, each vertex, and I'm going to couple them using ZZ interactions on the edges. And what this entails is that all the spins want to be aligned. Essentially, like there's two ground states, either all zeros or all ones, and in some sense, this just means that the 2D ferromagnetic Ising model is a repetition code, or some version of a repetition code. The toy picture you should have in mind, I should say, what makes this special is that if you paint an island of ones, which are the red bits, around a sea of zeros, then the energy of that configuration is proportional to the perimeter of this cluster. So in some sense, the energy cost grows with the number of bits you flip.
And this doesn't work in 1D, right? In 1D, the island could.
Yeah, exactly. In some sense, the picture you should have in mind is the following energy landscape where you have these two energy wells, and you can encode, or around all zeros and around all ones, and you can encode a bit using something like a thermal distribution around all zeros instead of using both energy wells. Of course, this is a quantum workshop, and the quantum analog of this would be the four-dimensional toric code. Now, this is 4D, so there's vertices, edges, squares, cubes, and tesseracts. I've just rendered a 3D cross-section. And we're going to place qubits on the squares and X checks on the edges. Also Z checks on the cubes, but that's not immediately important. So pictured, here's an edge. In 3D, there's 4 faces adjacent to that edge, and I'm going to put X's on those 4 squares. But what makes the 4D toric code special is that the parity checks have redundancies. So in particular, if you look at the neighborhood of any single site in this lattice, in 3D, there's 6 edges incident on that site. And you can convince yourself that if you take the product of the stabilizers associated to those 6 checks, they touch all the squares twice, so they cancel. So in other words, the product of these parity checks is always 1. So there's a redundancy between the parity checks. They're linearly not, or linearly dependent. In the particular case of the toric code, what this entails is that not all syndrome patterns are valid, only some of them, in particular those which form cycles in the graph. This will be relevant quite soon. Great, so thank you for your patience. I can now get to the actual question we study. And effectively, what we ask here is, how do we genuinely prepare these metastable memory states? And this is loosely inspired by a question posed by Aliki and the Horodetsky family on their original paper of the stability of the toric code. So here's a conjecture. Suppose you run the noise process, like this local quantum Gibbs sampler, initialized from a ground state, namely the bottom of the energy well. The conjecture is that the dynamics starting from the ground state is expected to undergo two stages. First, you remarkably rapidly converge to the metastable state, slightly above in the neighborhood of this ground state, in either polynomial or even polylog time. And subsequently, this state is then approximately stationary for exponential time, slowly leaking out logical information to the other half. Just to put this in another picture, you initialize the system in this like syndrome zero space, and in polylog time or poly-n time, the syndrome distribution thermalizes. And since the logical information is so non-local, it only slowly degrades in exponential time to the global Gibbs state.
Thiago, how are you setting data?
Oh yeah, this is all low temperatures. I should have said that more clearly. Essentially, like, the fact that it's stable is because it's at low temperatures. So this is, in some sense, asking for a Markov chain which at low temperatures has tiny spectral gap. It's really slow to mix, but there's still a fast mixing phenomenon from a specific initialization. Good. Yeah, so I guess repeating that message, in some sense, what we're asking here is like the mechanism behind the stability for the ground state. The ground state is actually quickly converging to a metastable state, which is then approximately stationary. And yet it like still has well-defined logical information. Good. Are there any questions about the conjecture? This first half of the like two-stage process is like essentially the title of the talk, the rapid mixing within a sector.
What is the Hamiltonian, the ground state, like is it different from the Hamiltonian?
No, it's the same one, yeah. In particular, like it's, in the Ising setting, it would just be this like ZZ, and in the toric code, you have like X and Z components, but they're acting on like the neighborhood of an edge or the support of a cube.
Sorry, for the quantum memory, you want the exponential time to go from one sector to the other, but do you really need the rapid mixing within the sector?
No, I mean, that's a good point. When it comes to thermal stability, just the fact that you're preserving information, then yeah, you don't need the rapid mixing component. I guess it's like, what we're asking here is to try to explain the stability of the ground state by quickly converging to something which doesn't change or takes a long time to change.
So in cosmology, when the energy is positive, there's like no Hare theorems, which basically prove exactly this. Like for those of you who know about de Sitter space, right? It empties out very quickly, but then if there's another cosmology that it can tunnel to, like you get exactly this dynamics. There's a
Oh, that's cool.
no Hare theorem, and then exponential time you tunnel. We should talk more about that if you're interested.
Yeah, I would love to hear. I think I've thought about this problem for a very long while, and new techniques to approach it would be very nice. That said, I should say that being quantitative about what state it is converging to is quite challenging in general. Okay, good. So I guess as I'm hinting at, unfortunately, we cannot show this conjecture in general, at least not for single site dynamics. But nevertheless, I will give some evidence that this is what's happening for the 4D toric code, as I'll discuss shortly. Good. So before getting into many more concrete details about what we can prove, I wanted to say some brief words and like gloss over about why I think this is interesting and to give some further motivation. I think there's generically two points or two perspectives of interest. The first one is the Gibbs sampling perspective. At least currently, in terms of provable mixing time guarantees, we only really have quantum Gibbs samplers in two like extreme regimes. Either the high temperature regime, where oftentimes one can rely on the fact that the state that you're preparing has generically no entanglement or just behaves semi-classically. And for this, I'll point you to some recent work by Ewan. And in the other extreme is the low temperature regime, where the only systems we really know how to prove anything about are either integrable, their spectra is explicit, and we don't really have, or like, there's no phase transition. So there's nothing really special about low temperature at all. The algorithm just works at all temperatures. And you're not really leveraging the structure of the low temperature problem, I suppose. Yeah, here I should also pause and say, I suppose what's special about this low temperature regime is that it really relies on new techniques like spectral methods or fancier techniques like spectral independence or like entropic inequalities. They're really tailored to worst case initializations, where here the initialization is crucial. There's no way to get like fast mixing from a generic starting point because you can always cook up a worst case starting point which mixes slowly.
And so can you to remind us, in 2 and 3 dimensions, the conjecture that you're trying to prove about the 4D toric code is just known to be false?
Yes.
Okay, thank you.
I mean, in 2D, there's no thermal stability.
Right.
Because it kind of behaves like 1D Ising models.
And then what happens in 3D?
Yeah, so in 3D, like the X checks are the same as 4D. So in some sense, Z observables are stable, but the converse is not. So it's a self-correcting classical memory in some sense. Still.
I see. So X observables are not stable.
Yeah.
I see. And but then Jungwon Ha, right, had this example in 3D where you're stable. Well, what was it? You're stable for polynomial time, but not for exponential time?
Yeah, that's a fantastic example. What they do is allow the temperature to depend on system size. So here we're like fixing the temperature, then we scale the system.
I see. Thank you.
Good. So the second perspective is quantum error correction, where it seems like asking these dynamic questions kind of leads to a fine-grained understanding of static and dynamic structural properties of quantum error correcting codes, as will become clear shortly. And the second point of interest is that, and really what led us to this project in the first place, are connections to quantum fault tolerance, which hopefully I'll have time to get into at the end. Great. So with that in mind, what do we prove? Well, we prove that at sufficiently low temperatures, or high enough inverse temperatures, we give like a Markov chain, a Lindblad evolution for the 4D toric code, which is quasi-local in the sense that the updates act on log size blocks. And when initialized from the ground state, it rapidly mixes in polylog time to this Gibbs state within a sector, this like metastable distribution around the ground state. Great. I should say that I stated this for the 4D toric code just to be specific, but the proof approach is quite broad and it works for like a wide class of self-correcting memories on lattices, technically whose thermal stability is based on parity check redundancies. Are there any questions about the theorem statement?
Can you remind me what's the definition of sigma phi?
Yeah, it's like the Gibbs state within a logical sector, like it's the Gibbs state condition on lying in half of the energy well.
Is it projection?
It is a projection onto the Gibbs state, yeah.
Maybe for someone who's seeing these theorems for a couple, how should I interpret this quasi-local property? Like, do I want it to be fully local where each jump only acts on a constant number of qubits?
Yeah, that's a fantastic point and something I should comment on now. In some sense, this theorem statement is a little dissatisfying. Like what I really want is single site dynamics. If you ask this question to a classical Markov chain person, like the real open question, the hard problem here is about single site dynamics. But as will become clear shortly, there are some clear technical issues towards getting that to work, which I'll pose essentially as open problems.
But intuitively, if your error only, I'm assuming this is kind of modeling the noise that's happening to your memory. If your error acts on fewer qubits and you prove something where the error acts on more qubits, isn't that better?
Yeah, I mean, that's good intuition, but somehow what you'd like to say is that like during the evolution of like the single site dynamics, it's hard to argue that due to some like unlikely but plausible occasion, the errors don't compound in some like plausible but contrived way. Whereas when you do like log local dynamics, you can kind of argue that within the interior of the block, the noise is really well behaved. But don't worry, this will be clear shortly. With that said, this result, or I still find this result interesting because it still allows us to claim a dichotomy of a Markov chain which doesn't mix quickly in general, but from a specific starting point, does have some rapid form of convergence. Great. So I should also say a very nice, cute application, which was pointed to me by some physicists, which is a characterization of quantum phases within self-correcting quantum memories. So some in the condensed or like many body physics literature would say that two mixed states are said to be in the same phase if there exists a pair of quasi-local channels which map sigma to rho and rho to sigma. And here the quasi-locality is relevant because it allows you to leverage like Lieb-Robinson bounds to relate their correlations, for instance. And in this context, we're able to establish that for this class of self-correcting memories on lattices, the ground state is connected to, we exhibit this two-way connectivity from the ground state to the Gibbs state within a sector, where one of the directions is guaranteed by the Lindbladian evolution of the theorem statement, and the converse channel is guaranteed by the existence of a local decoder, or a parallel local decoder, let's say, which you could extract from the original works on these codes. There's a brief comment that although the Lindbladian evolution is quasi-local, you can simulate the entire process on a quantum computer using 2 qubit gates, at least specifically for the toric code, like using a low depth, polylog depth quantum circuit, geometrically local in the dimension of the lattice. Great. So today's outline, depending time permitting, well, essentially I'll start by posing the main technical challenge, which is establishing that the ground state is thermally stable in the first place. I'll then point out arguably the main technical tool, which are in some sense new versions of decay of correlations for states at low temperatures, which could find some independent interest. I'll then explain the algorithm and the main outline of the rapid mixing argument. And time permitting, I'll conclude with some applications to quantum fault tolerance. Nice. So just for concreteness, what does the Markov chain for the 4D toric code look like? So here's a cross-section of the 3D, like a 3D cross-section of the toric code, where I've drawn a bunch of syndrome configurations, which, as you should recall, are just loops on the lattice. And a single site update can essentially create a new loop or annihilate a loop, or it could extend or contract loops, but curiously, it could also merge adjacent loop configurations. Broadly speaking, this is what the Markov chain looks like. And with that in mind, here's a very concrete question. Can you show that the memory time, the amount of time it takes to escape the well, like an energy well, for the 4D toric code, when initialized from the ground state, is at least as much as starting from thermal distribution slightly above the ground state? And this, perhaps rather surprisingly, is still open for a wide class of classical and quantum memories. It's instructive to take a step back here and really kind of try to understand what this is asking.
Wait, sorry, what is the memory time if you start from the ground state? Because if you're in the ground state, that means you've already mixed, right? So you've lost your memory. I don't understand.
No, it's starting from a ground state. So I guess let me be more specific.
Oh.
If you think about the Ising model and I initialize it from all zeros, how long does it take for the majority to flip?
Okay, good. And then what's the metastable state in contrast to that?
It's the fraction of the Gibbs state with majority zeros. So in other words, you have the thermal distribution over syndromes.
Okay, got it. Thank you.
Yeah. And I guess what I'm getting at, and I may have kind of glossed over here, is that this question is only really known for a class of Glauber dynamics or a class of models known as monotone models, such as the Ising model. But the same question for the Potts model, which is just the Ising model with 3 colors, is still open. And really what I'd like to highlight here is addressing this question is crucial to rapid mixing. There's no way you can get rapid mixing from the ground state if you can't even establish that the ground state is stable. And in our review of the literature, what we found is that the original paper on the thermal stability of the 4D toric code is remarkably commonly misquoted to have proved the stability of the ground state, where what actually they proved is the stability of the metastable thermal distribution, which is already in some form of thermal equilibrium. Good. So just to return to the question, effectively what we're asking here is there some, or like, can you rigorously rule out the existence of a shortcut if you were to initialize from the ground state, where you're kind of either forced to go through the metastable distribution, or can you somehow tunnel out from the bottom of the well? And this is curiously related, or I guess in some sense what this is really asking is whether lower temperature states can heat up quicker than higher temperature states, which is somewhat curiously related to like the reverse of the Mpemba effect. Which famously, the Mpemba effect famously states that higher temperature water can cool down quicker than lower temperature water. And this is just asking, can you rule out a converse to this? Of course, the name isn't too important. What's really important here is that there's a concrete technical question. And my personal belief is that whatever new proof techniques that you develop to prove this will also give you rapid mixing. And yeah.
Does the toric code have this threshold temperature like the icing model does?
There is some threshold for thermal stability.
So there's some constant temperature that's below that.
Yes, yeah.
And the metastable state is defined in terms of the thermal state at that temperature.
Yes, yeah. Yeah, precisely.
When you use the phrase rapid mixing, you mean rapid mixing to the metastable state that you then stay at for exponential time?
Yeah. I should say mixing within a sector or within a phase.
All right, I got it.
Cool. I should say that it is actually possible to rule this out on expander graphs, but the question is still open for lattices. And just to highlight perhaps the depth of the question, the same question for the Potts model, which is just Ising model with 3 colors, is still open. And there's some belief that the Potts model should be the simplest setting where this should be tractable. Great. So with that in mind, I can now get to the main technical tool. So the starting point of our work is what I find to be an extremely elegant paper by Ghessari and Sinclair, where what they showed was that if you look at the fraction of the Gibbs distribution of the Ising model, conditioned on having majority zeros, so again, this is like half of the energy well, they established precisely this phenomenon where at sufficiently low temperatures, single site Glauber dynamics, starting from the all zero string, rapidly converges to this Gibbs distribution within a phase, Gibbs distribution with majority zeros in essentially polylog time, which again is then stable for e to the square root n time. And perhaps their key insight is the following. The Gibbs distribution, the global Gibbs distribution of the Ising model, 2D Ising model, does not satisfy any meaningful notion of decay of correlations. In particular, you could think about the ground state, where if you see a 0, any other bit will also be 0. Like the bits are maximally correlated. However, one of their key observations is that the Gibbs distribution, conditioned on having majority zeros, does have decay of correlations. And so in particular, the way that they quantify that is using this notion of weak spatial mixing, where the idea is to compare 2 marginal distributions, where the first marginal distribution is this Gibbs distribution conditioned on having majority zeros, but we're only going to look at a single bit at the center of some box. Here in the picture, I've drawn like a bunch of little clusters of 1s inside a sea of zeros. And this is going to be compared to the global Gibbs distribution, but where you pin the boundaries of some box of size L to zeros. So in some sense, by pinning the boundaries of the box to zeros, you're kind of like fixing the interior to have a well-defined preferred direction. And the claim, I guess I didn't write it quantitatively, but are that these 2 distributions are exponentially close. These 2 single bit marginal distributions are exponentially close. Now, what's the intuition for this statement? It's really that at low enough temperatures, the clusters of syndromes or 1s of errors are really sparse and they're localized. And the only way these 2 distributions could possibly differ is if you have some large cluster of 1s which spans from the boundary on the left-hand side all the way to the center. Good. With that in mind, one of our technical contributions is developing the same type of statement for the syndrome distribution of the error correcting code. Of course, it's not immediately clear how you would condition on qubits, at least in a quantum setting, but conditioning on syndromes is well defined because in some sense it's like a commuting Hamiltonian. You can condition on like the eigenvalues, I suppose. And what our claim is that for this class of self-correcting memories, so long as that you're at a sufficiently low temperature, the marginal distribution at any specific syndrome U, in this case like an edge in the 4D lattice, does have, or like, you know, the marginal distribution at U of this syndrome distribution, Gibbs distribution over syndromes can be compared to the marginal distribution at U, where we pin the syndromes of the boundary of this box to 0, where the notion of closeness is exponentially small in the size of the box and the gap to the critical temperature. Now, I should really pause here and make sure everyone understands this definition because it's arguably one of the more important parts of the talk. Are there any questions about what it's saying or what it's saying or why it should hold?
So I can just think of this as of all of the possible errors that can happen, the errors usually don't touch both the boundary and the interior simultaneously.
Yeah, that's the big picture, yeah.
Sorry, I just forgot this in the previous slide. What was the superscript 0 on pi beta in this slide?
Yeah, good. So previously I was talking about the distribution over spins of the Ising model. I guess I should have relabeled the pi's, but here in this setting, I'm just talking about the distribution over syndromes. Yeah, I guess I can write it down. There's a very explicit form. For any syndrome S, it's just e to the minus beta of the Hamming weight of S divided by some normalization, which are the set of valid syndromes. So yeah, in particular, the way you should picture this is that you have a collection of loops in the 4D lattice, and it's exponentially weighted in the total perimeter size.
That exponential, the L times beta minus beta star, that's independent of dimensionality?
Yes, yeah. Yeah, there's no n dependence, no prefactor either. It's just L. And the constant is 2. Yeah, so I should say here that the constant temperature that we find is probably not the correct critical temperature for the onset of self-correction. In particular, to the extent of our knowledge, there's no rigorous analysis of what the precise critical temperature of the 4D toric code is. And even if there were, our analysis should not get the correct temperature for the onset of decay of correlations, that is. And the work we're based on, perhaps they do a lot more work to rigorously get the correct bounds up to the critical temperature. Good. So
sorry, this is ignorant, but it feels weird that you're getting good results above a temperature. It feels below, the colder you are, the more self-correcting you should be. But is this just an instance of the problem you were talking about earlier, monotonicity?
No, it's really how it works. The colder you get, the more spins are aligned.
Yeah.
So you expect the clusters of ones to be tinier and tinier, right?
That's an inverse
Beta is
temperature.
inverse temperature.
Oh,
Yeah.
I made the same
oh,
mistake when you
okay.
did it before.
Oh, good. Thank you.
Okay. So yeah, as I was getting at earlier, this holds for a wide class of self-correcting quantum memories. In particular, anything this very nice work by Bombin et al. Would call satisfies a connectedness criterion, which just kind of stipulates that syndromes are clustered together. Cool. And I should also say that at a technical level, what we actually need is something slightly stronger than this, a notion of strong spatial mixing. In some sense, weak spatial mixing quantifies the decay of like point to set correlations, like the set being the boundary, the point being the center. Strong spatial mixing quantifies perturbations of boundaries, but I won't really get into detail on that. I will, however, for anyone interested, kind of sketch how the argument works, because the proof technique is kind of cute. The basic idea is this, or like the key concept is this notion of a separating surface of syndromes. In particular, a separating surface on the lattice is just a collection of edges. And those edges have two properties, or that set of edges has two properties. First, it disconnects the center spin from the rest of the lattice, so it literally separates the center spin. And second, for any set of syndromes on this lattice, all the edges on this surface are 0. So in particular, it is a screen of unviolated syndromes around U. And the analysis then proceeds in two claims. The first claim is that if you were to draw two samples from the two distributions that we're trying to compare, then they both agree on a separating surface with high probability. And I won't sketch this claim, but perhaps believe it from the previous intuition of how syndromes cluster. And then the crucial idea is that since they agree on the surface, you can kind of couple the interior configuration using a Markov property. I should say here that these like Gibbs distributions over syndromes, or like these metastable states, don't exactly satisfy a Markov property, but they satisfy some approximate notion, which is sufficient for the purposes. Great. How am I doing on time? So I wanted to say a few words about how the algorithm works. Oh, I guess I can take questions before moving on. Great. So the algorithm. The algorithm proceeds in two relaxations, two single site dynamics, where the first relaxation is kind of this standard trick to avoid systems without monotonicity, or systems that aren't monotone in the classical literature, which is block dynamics. So essentially what block dynamics is that I'm gonna pick a center spin chosen uniformly at random from the lattice, and I'm gonna consider a little box around it. Then the idea is to resample the entire interior of the box, conditional on what's currently at the boundaries. This is also known as heat bath block dynamics. It's essentially kind of connecting to Sunny's question earlier, ensuring that everything inside the box is already drawn from the Gibbs distribution, or some version of it conditioned on what's currently at the boundary. Now, one of the starting points for our analysis is this very nice paper by Dyer, Sinclair, Vigoda, and Weitz, where they established that if you have this like strong spatial mixing condition, this strong decay of correlations property, for every possible boundary pinning, then block dynamics mixes quickly, so long as the block size is sufficiently large. And I should say here that this is very much a high temperature result. And in some sense, our analysis can be interpreted as a low temperature version of their statement. However, unfortunately, in our setting, we don't actually have the guarantee of decay of correlations for all possible boundary conditions. We only really have decay of correlations for boundaries that look like the ground state. And at a quantitative level, the way this manifests is that it's really hard to rule out configurations where the boundaries kind of, you have like some bad boundary condition during the algorithm, and that enables like a proliferation of errors where bad boundaries kind of compound and become worse and worse. And I guess in a picture, on the left-hand side, we have some like configuration of spins, where configuration of syndromes, where some syndromes enter the box. And then after one update, the syndrome configurations have grown and like they've merged together. And it's really hard to like rigorously rule this out. So the way we kind of sidestep this is a variant of block dynamics, which in some senses is inspired by decoding algorithms, which very simply can be described in the following. Again, from some starting point on the left-hand side, we're going to consider all the syndrome configurations contained entirely in the box. In other words, the cycle of syndromes does not hit the boundary. And we're just going to erase all of the ones inside, and while fixing the ones on the boundary. In some sense, kind of like applying a decoding operation inside the box. And subsequently, condition on everything that's in the box and touching the box, we resample the configuration inside. Now, it's okay if this is not immediately clear to you what the algorithm is doing. In effect, all we're really saying here is that we kind of have this modification to block dynamics, which gives us control over the boundaries to allow us to have decay of correlations throughout the algorithm. Good. So just to say a sentence or two about how the analysis goes, the basic idea behind the analysis is to consider a fraction of the state space where all the loops are small. In particular, all the connected components of syndrome configurations are clustered. And the idea is that inside this truncation to the state space, even though it's a small fraction of the entire state space, it still has most of the mass of the Gibbs distribution, so long as the temperatures are tuned correctly. And then the analysis then proceeds in the dichotomy I was mentioning earlier, where we first claim that if you start from a specific state, in particular the ground state, it actually takes an exponential time to leave this good fraction of the state space. And we combine that with a coupling argument, which essentially says that within this good fraction of the state space, you still mix quickly. I won't actually sketch how either of these statements work, but I guess the big picture is to exhibit this dichotomy where, to avoid like the overhead of spectral methods, you just exhibit this good cut of the state space, which takes a long time to leave, and yet mixes quickly within within that fraction of the state space. Okay. Let me pause here and ask if there's any questions about what the algorithm, yeah.
Is it detail balance?
Yes, within a larger fraction of the state space, it is detail balance.
Is it like exactly?
Yeah, it's exactly detail balance. Yeah. Yeah, that is very important, yeah. Any other questions? I think I can elaborate on that then, since we have time. Like the basic point is that once you've kind of pinned all the syndromes you're fixing, the update is just resampling from the Gibbs distribution. And that will always be detail balanced. So you can define like an ergodic component of the state space, like a fraction of the state space which is connected. And within that fraction, you're completely detail balanced. Great. Anything else? I should also comment here that like the role of the modification to the block dynamics is really captured in this memory lemma. Like in particular, in the beginning of the talk, I was saying how hard it is to establish stability of the ground state. By cheating and modifying the Markov chain, we are able to establish stability of the ground state. That's essentially the role, is to establish this like central second claim. Great. So in the few minutes I have left, oh, I didn't have a transition slide, is to comment on a conjecture which initially led us to this project in the first place. So here I do need to do a slight detour into state preparation. Broadly speaking, in fault-tolerant quantum computation, the first step to any quantum computation is to prepare an encoding of the input to that computation. So in particular, if the input of your quantum circuit contains a bunch of zero strings, the first step is to encode those zero strings into a logical zero string. And of course, there are many ways you could do that. So in the presence of noise, it's not immediately clear what it means to fault-tolerantly prepare the logical zero state, because since noise is like prevalent throughout the circuit, you're only going to prepare the logical zero state up to some residual noise, some local stochastic noise. So as I was getting at, there are many ways one could perform this type of fault-tolerant state preparation. Perhaps most notably, the approaches lie in two camps. The first camp is what I'd refer to as classically assisted, where the basic idea is you perform a collection of parity check measurements, and you then use a classical computer to process the information and apply some feedback operation. This is perhaps most known in the like lattice surgery literature. If you want a brief background of how this works, you could read the introduction of my paper with Yunqiao. And the second camp, or the second way you could do this, is using a concatenation scheme. So essentially, what this means is that the goal is to apply some encoding unitary to the all zero string. And the way that we do that fault tolerantly is to take that encoding unitary and encode that into a concatenated fault tolerance theorem. So here, a very nice review of how this works is in this paper by Fauzi et al. From last year. Effectively, what I'd like to conjecture here is a third route to fault-tolerant state preparation, which is based on running a quantum Gibbs sampler. So here's a very concrete conjecture. Suppose you take this noise process, which we've been talking about throughout the talk, and you just initialize it, or you just run it from an initial product state. The conjecture is that in polylog time, or rapidly poly-n time, you actually converge to the Gibbs state within a sector 0. So this fraction of the Gibbs state with a specific logical observable. In some sense, this would be some form of a state preparation, a robust state preparation for self-correcting quantum memories. Now, let me just briefly comment on why this is reasonable at all, or why this is interesting. You can kind of convince yourself, based on the picture in the previous slide, that this logic, this tensor product of all zeros, has a well-defined Pauli z observable, right? If you measure the tensor product of z's, you'll always get 0. And you can imagine initializing your algorithm or interpreting what the Gibbs sampler is doing as alternating parity check measurements with errors. So you could imagine that the initial state to your algorithm is just a logical 0 string with a high weight Pauli z applied, or a high weight z error, but no x error. And the question is, if that's your initial state, what does the algorithm lead to? And in some sense, there's two Markov chains happening here, two completely independent noise processes. One of them is the Z Markov chain corresponding to Z syndromes, which is initialized from the ground state. And this should be familiar because it's just the problem I talked about throughout this talk. But the second Markov chain is a completely different beast, where it's essentially like this Glauber dynamics, but initialized from a uniformly random string. And the conjecture is that this low temperature Markov chain, when initialized from a random string, mixes quickly.
I think I'm missing something basic here. So you're saying that there's no error correction here. You're saying that for every product state, for all 2 to the n of them, it's as if there's a potential with a minima around that.
Not exactly, but almost. Okay, so the error correcting code defines a Hamiltonian, and the Hamiltonian defines the dynamics. So the error correcting code is present. It's just not in the initial state. That's the first statement. You're essentially, you have a Glauber dynamics, right? Just think about the Ising model. In fact, it's best described in the following slide. What's the classical analog of this question? The classical analog of this question is you take the 2D Ising model at low temperatures and you initialize it from a uniformly random string. How long does it take to converge? That's the.
So I can't recover that I started with the all 0 string, but I can recover that I'm in whatever sector that's closest to that or something.
Yeah. So in particular, in some sense, the Markov chain that is happening in the quantum process is occurring over the syndromes of the code, and those syndromes behave like this classical question. And I apologize for the poor rendition of a 2D Ising model. Good. So in the few minutes that I have left, I wanted to comment on some future direction. So here there's really two questions that I find super interesting. The first one is the first point, where what models are there that where random initializations is tractable? And this oftentimes is referred to in the literature as phase ordering. And just a few days ago, maybe like a week, our collaborator, Reza, he had this paper saying that for the Potts model on expanders, or Ising-Potts model on expanders, you can show rapid mixing from a biased initialization. So initialization which is random and bounded away from uniform. So not exactly the infinite temperature limit, which I discussed on the previous slide, but as close to that as we possibly can get using current techniques. The other question, which I find most interesting, is the last point, which is, can you establish the stability of the ground state for the 4D toric code using single site dynamics? And in some sense, this is asking whether this like monotonicity obstruction, which I admittedly only high level mentioned throughout the talk, is really inherent to the argument, or whether, much like the Ising model, it's just a matter of finding the correct proof techniques. There's also some questions about understanding these dynamics at exactly 0 temperatures instead of constant temperatures. And in some sense, this connects to voter processes like majority dynamics, which has its own independent interest. And I'll skip the third point. Thank you very much.
We already had quite a few questions, but are there any more questions for Thiago?
Yeah, you said this already, but so the dynamics they're not the usual dynamics, but they're like some block version of the usual dynamics.
Yeah.
Okay, so it doesn't like depend on sector or anything.
No. Yeah, sorry, just to add to that, like if you were to initialize the system in a random ground state and run the dynamics, it would converge to the global Gibbs state.
I'm wondering if you can say something about like what the particular Lindbladian that you proved your result for looks like, in particular, like, can I think of it? Is there some environment model for that Lindbladian?
Yeah, I mean, it's relatively simple to describe as a channel. Essentially what it does is that it picks a random site, it measures all the parity checks around that site. It looks at all the syndrome, like connected components of syndromes entering the box, and it just doesn't touch them. And it updates the syndrome inside the box according to like the conditional measure on the boundary. So this is a channel, it's not a Lindbladian, but there's a standard way to convert discrete channels to like continuous time Lindbladians, and we just leverage that.
Okay. And I mean, at the very beginning of the talk, you had some intuition, which is like, you thought that like, it seemed like you would expect for generic quasi-local Lindbladians, something should happen. So like, what's the obstruction? Like that Lindbladian you described as doing something very specific, right?
Yeah, that's true.
What's the like obstruction to showing it for more general or, typical Lindbladians in whatever sense of typical you prefer?
Yeah, I mean, as long as it's detailed balance, the obstruction is very clear, right? Like you would like to leverage decay of correlations, but you don't have decay of correlations for every boundary condition. So somehow you'd like to argue that during the evolution of the algorithm, you only encounter good boundaries which have decay of correlation, and that's hard to maintain over time. So if there's a new way to maintain some form of invariant, like a monotone invariant, where the boundaries are always good, then you could plausibly generalize the approach.
Okay, so if I could like come up with some conserved charge which does this, and then it's always Lindbladians that respect that conserved charge. I mean, I guess in that case you wouldn't get it would never converge to the overall thermal state.
Or just leaks slowly.
Yeah,
sure.
Okay. So I remember, this question came up like 20 years ago or more, but in case things have changed, like I want to ask it again. Like, would it be easier to build a quantum computer in practice if we had another spatial dimension? Like, if would this actually help? Like, if we could build the 4D toric code, would that be like, has nature been cruel to us by giving us only these 3 dimensions?
Why are you assuming the interaction graph has to do with the actual dimension?
Well, okay. I mean, of course, you can try to build a non-local interaction graph, but you know, and some people have tried. The group at IBM is trying to do that, but that's hard as an engineering matter. Right? I mean, you know, like, is this like a thing of theoretical interest, or is it more that like, wow, like this would, you know, if you had a 3D version of the toric code, this would actually, you know, that was self-correcting, this would actually make it much easier to build a quantum computer.
Yeah, I mean, what I can say is there's a lot of active interest in finding a 3D self-correcting memory.
Yeah.
And that seems to be an outstanding open question. Whether or not it would help you build a quantum computer presumably depends on how you implement gates too.
Yeah.
So,
yeah, good.
Any more questions for Thiago? Okay, if that's not the case, let's thank Thiago again for the very nice talk. And we have a little coffee break, and we reconvene at 11 for a talk by Anthony.